Hello, and once again, welcome to the organic spectroscopy problem series. This is video number 3, SS3 party here. And in this program also, I will discuss some of the past net get questions like the previous videos, 2 videos, and this is the third one. The first question is very, very simple. I told you when you learn or you watch the video, pause it, answer it, then tally with my answer. So how many carbon signals, decoupled, proton decoupled carbon signals that benzonitrile can have? Obviously there are how many non-equivalent carbon? So cyanide carbon is 1, this quaternary carbon is 2, and these orthocarbons are equivalent 3, and these metacarbons are equivalent 4, and paracarbon is another non-equivalent carbon. So altogether the carbon 13 NMR will show 5 singlets in the decoupled spectrum, proton decoupled spectrum in their respective places. You know the range of carbon 13 is very, very wide, 0 to 250 ppm, and cyanide the reason is about 130 140 like that, cyanide carbon. Let me remind you the different ranges of different types of functional groups and groups, other groups also. Now these are the carbon from the sp3 hybridized carbon, CH3, then CH2C, and the carbon joining with halogen little more and go up to 80. This C triple bond N that we are looking for is about 110 to 130. This is the region, and the alkyne region is little less, about 60 to 100. The alkene and aromatic region, they overlap. Downfield region, this is 90 to 160, this is 90 to 160 70. So these are overlapping areas for alkene carbon and the aromatic carbon. And the aldehyde ketone is the most downfield, above 200, 190 200, I'm sorry. And the carboxylic is 170, 180, 190, and derivatives also in the same region, 190. Maximum can go up to 100, 200, but 200 aldehyde and ketones, they will exceed many times 200, maybe 190, 95. So carboxylic acid is first, then its derivatives, and then the most distilled is the aldehyde and ketones, right? So just I'm reminding you these different ranges, and they go to the second one, which is on IR, infrared spectra. And among the compounds given below, the one which exhibits a SAR band at around 3300, remember this SAR, had it been a OH group, the OH stretching because of hydrogen bonding interaction, it will give a broad band. So this SAR band always speaks of the CH stretching for the SP, I repeat, sp hybrid carbon, this terminal alkyne. So out of the 4 possibilities, this is but1-wine has a terminal CH bonded to sp hybrid carbon that will have a stretching frequency of 3300 centimeter inverse. We say frequency, but really it is wave number. That is the common convention that we use while talking. We say frequency, but writing it is wave number. So and I remind you that if it is a sp2 hybrid carbon CH stretching, then it will be slightly above 3000. That is an aromatics and alkene. And if it is a sp3 hybrid CH, then it is little less than 3000. It's 2900 some odd. So with this we go to the third one, which is very, very interesting. Third one, contains three magnetic nuclei, proton, fluorine, and phosphorus. There are two phosphorus atoms. So the question says, in this compound, the correct pair of proton and 31 phosphorus NMR spectral patterns is this. Now, the first choice is the triplet for proton pick and doublet for phosphorus pick. And the second one is a doublet of triplet. This is DT for the proton pick, and doublet of doublets is for the phosphorus pick. Third choice is doublet and triplet. And this is triplet, triplet, and this is triplet, doublet. Let's see what is the correct answer. Now, let us first take up. Now, before that, let me remind you that in a 2.3 Tesla field, for example, proton resonates at around 100 megahertz. That is the Larmor frequency for proton resonance. But the same field, the phosphorus 31 resonance occurs at a different place. Fluorine also resonates at a different 92 point something. Here there is no fluorine resonance. That is why I have not recorded 92 point something. So phosphorus 31 resonates at 40.5 megahertz, around that, depending on the electronic environment. Now, let us first talk about the proton NMR signal. Now, this proton is coupled with fluorine as well as the two phosphorus atoms. And the coupling constant is called J2. 1, 2, 1, 2. 1, 2. So these coupling constants are J2, and if you do not remember that J2 values of hydrogen and fluorine coupling is the very high, and phosphorus hydrogen is very low, just the opposite. J2HF is about 40 to 60, 70, 80, 20 to 80. So I've taken a common value of 60 Hz, for example. And the phosphorus hydrogen, phosphorus proton J2 is very small, 1 to 5, so I have taken 3. Supposing you don't remember, doesn't matter, you take any one bigger J, the other one smaller J. They can't be equal, right? So I told you during my deliberation, I will be sharing many things with you so that you enrich your experience with organic spectroscopy and solving problems. Now, the usual convention of studying, analyzing the pattern for a particular pick, NMR pick, is to go for the splitting with a larger coupling constant, the larger J value. And then each of the components of the first multiplet that you do theoretically in a piece of paper, then you split each component into the required number of multiplet with the other smaller J value. Since the J value for the HF is larger, about 60, so let us first split the proton pick into a doublet with a larger coupling constant, and each of the component is again split by 2 phosphorus atoms into a triplet, 2 plus 1 triplet. So with a smaller coupling constant 3. So this will be called the doublet of triplets. You know the convention how to name a multiplet of multiplets. The first multiplet will be named after the larger coupling constant. The next, with a plural S, will be named after the smaller coupling constant. So the first one is the doublet, which has a larger coupling constant, and the triplet has a smaller coupling constant, so that will come later, and with S, plural. So it is doublet of triplets, DT, right? Now, this is the pattern that is to be found in the spectrum. This is a triplet. Oh, I have forgotten to use this one. So this is a triplet. This is another triplet. So there are 6 lines altogether, and the separation between the midpoint and midpoint is the larger J. This one is the larger J, and you know this one is the smaller J. And how to calculate, I will take another video to show you how you can calculate J values of a complex multiplet, multiplet of multiplets, or simply multiplet of multiplets. So to find and take the average, so J smaller, that is what we say 3, J smaller can be found out the difference between 1 and 2 peak, or between 2 to 3, which are identical. Not 3 to 4, or 4 to 5, or 5 to 6. In fact, all these 4 values are taken and averaged. The average value is expressed, right? And the larger coupling constant is between this point to this point. That means if you go one place left, then also go one place left. So it is the difference between first peak and the fourth peak, or second peak and fifth peak, same, or the third peak and sixth peak. So they will give you the same result, a similar result, very close to each other. So there will be some experimental, the error, or in the NMR spectrum, you don't get always a 100% first order spectrum. So you have to average these values and get the bigger one and smaller one. So the proton peak is a doublet of triplet. And obviously, if you go for phosphorus peak, these two are equivalent. So anyone you can check for our analysis. So this phosphorus is J2 coupled with proton and J2 coupled with fluorine. Presume that phosphorus fluorine has a larger coupling constant, because we already know phosphorus hydrogen J2 coupling constant is very small. So if we presume that the J2P and F is larger, then it will be split into a doublet, theoretical doublet with a larger coupling constant, and then with a smaller coupling constant, then it is a DD, doublet of doublet. I have shown you this is PF, which is presumed to be larger. Value is not given to you, so you just presume that it is larger, and each of the component will be split into a smaller coupling constant. It contains 4 lines, but 1:1:1:1. This is a small doublet, this is a small, this you see, this is a small doublet, this is a small doublet. The midpoint and midpoint difference is the large coupling constant, and the small peaks between the first doublet is the small j. So also the separation between the third and fourth. Now to find out the average, you have to take 1, 2 and 3, 4. They will give you smaller, the average. And for larger coupling constant, 1, 3, which is equal to 2, 4. They will give slightly different values, and you average it to get the best, with least standard error. Now coming to the fourth one, which is really, really interesting. Now the fourth one is I have just converted the question into a determination of structure. This same question has been taken from either NET or GATE previous years, maybe last 5 to 7 years. I was scanning through, browsing through, I got this. Now I have not given you the choice in the beginning, I have given it at the end. It says that the formula of the compound is C10H12O, shows the characteristic spectral data given, identify the compound and assign each proton resonance values, and explain the multiplicity of the aromatic protons. Now obviously, the IR is 1690. What does it tell you? 1690 tells you, first you have to find out from the molecular formula, we find out the DBE, double bond equivalent or on saturation, is 5. Carbon minus hydrogen by 2 plus 1, it is 5. 5 means there is an aromatic ring, benzene ring, that itself consumes dB of 4, and one more double bond will be there as a substituent. So benzene ring plus another double bond, that will be meeting the 5 demand of BDE5. Now once we know there is an aromatic compound with one more, there is a suspicion that this could be a ketone, because there is only one oxygen. It can be ketone or aldehyde. There is no aldehyde proton peak in the proton NMR. About 9 to 11, there is no peak, downfield peak. So it has to be a ketone. So the double bond O will be adding another dBe, making it 5. Now this, let me read out from the lowest ppm to the highest ppm, 1.3, 3 proton triplet, coupling constant is 7.2. Then 2.41, 2 proton quartet, same coupling constant. 2.32, very close, again 3 proton but singlet. Then coming to the aromatic region, which is very interesting, 7.44 is 1 proton triplet, 7.57 1 proton doublet of triplets DT with a coupling constant of 7, large bigger and smaller is 3. Obviously this is J3 and this is J4. J5 is almost 0. And the other one is 7.77 ppm, 1 proton. This is simply triplet with a smaller J value, J4 value, and 7.9 1 proton, again a doublet of triplets, 7 and 3. So, and most important, the electron impact mass spectrometry gives you the base peak 119 and another very prominent peak at 57. So that is the game changer. You will see this will be the game changer. You have to identify and assign all the picks. So dB, BD is 5, IR spectra suggestive of aromatic ketone. Now from the 4 1 proton aromatic picks, 1H, 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 4 protons aromatic peak suggests it is a disubstituted compound. And that too either ortho or meta, cannot be para, because the para disubstituted compound will have only 2 non-equivalent categories of protons, A2, X2. These two are equivalent by symmetry operation, exchangeable, interchangeable, so also this. So, but they are not magnetically equivalent, so there is a J3 coupling and J4 coupling, but already know that chemical equivalent protons that do not spin couple. This will couple with this to give a doublet, and each of the doublet components will be split by a J5, not with this, the J5 of 0 Hz. So it will be virtually giving a doublet. A2 is virtually a A2X2 system because the J5 is almost 0. Now X will give you another doublet, because you take X or X, this is a doublet J3, and these two will not couple with each other, they are chemical equivalent, and J5 is 0. So both of them will give you a doublet at the respective positions depending on the nature of X and Y. Forget about it. We have 4 non-equivalent proton picks in the aromatic region, so it has to be ortho or meta. So the data suggests that the aromatic in the J value is 7 and J3 value is 7 and J4 value is 3. Now the 3 proton triplet and 2 proton quartet suggests of an ethyl group, undoubtedly an ethyl group. This is 3 proton quartet and this is 2 protons quartet, and this is 3 protons triplet and this is 2 protons quartet. So that indicates of an ethyl group. So this 3 proton 1.3 ppm is for this and 2.42 ppm is for this. So ethyl group is a must. So let us combine, try to list what are the part structures that we have so far got. One is the benzene ring, disubstitution, ortho or meta, carbonyl group, that is a ketone, and an ethyl group. And by adding all the carbons, we are left with one more carbon. It is 9. 6 plus 1 plus 2, 9. So the remaining carbon, one carbon, must be in the form of CH3, because there is a CH3 singlet also. There is a CH3 triplet as well as a CH3 singlet. So this CH3 singlet at 2.32 is definitely this one, suggestive of a CH3 group bonded to either the keto group or benzene ring. Because there are two possibilities. Either the ethyl group is there in the ketone, the other part, methyl group is in the ortho position, or methyl group is in the ketone position, so that this will be 2.4, 2.3, and this is ethyl, 2 protons quartet, 3 protons triplet. So there are two ortho possibilities. This is quartet, this is triplet, this is singlet. This is singlet, and very interestingly, the singlet of CH3 adjacent to a aromatic carbonyl group is about 2.4, and this CH3 bonded directly to the benzene ring is about the same 2.2, 2.3. This is little more, this is little less. It's very difficult, to. And so also this is quartet, this is same 2.4, 2.4, 2.5, and so also here. So it's very difficult to rule out one and take the other. The meta possibility is similar: methyl, ethyl, methyl, ethyl. Now what to do? Whether it is meta or ortho. If it is meta, then you have to select with which meta. If it is ortho, then which ortho. Now for that we have to look to aromatic peaks. Now supposing it is ortho, anyone, either ethyl here, methyl here, or ethyl here, methyl here, whatever. We are interested in analyzing the pattern for the aromatic protons. Now this proton has a J3 coupling with 7 Hz and a J4 coupling of 3 Hz. Would be a DD. J5, there is no data, so we presume J5 to be 0. Right? So this should be a DD. This is the expectation. If this one, it will be the structure. Ortho, any one of the ortho. And this one will be a triplet. J3, there are two J3 on either side of this. So there will be a triplet and there will be a J4 here. So this will be a triplet of doublet TD. TD, first T, then T. This will be a triplet with a bigger coupling constant 7, and then J4 coupling small, it will be a doublet, so TD. And this one also a TD. There are two J3 coupled protons and then a meta, that is J4 coupled protons. It should be a TD, and this one should be a DD with J3 coupled and J4 coupled. So just like this DD, this is also DD, and these two are TDs, right? But at the respective positions, we are not interested in that. We are interested in the patterns, but we don't find, although there are two, there are no in the actual data. There is no TD. There are two DTs. See these data: DT, doublet of triplet. Doublet of triplet. There are two DTs, not TDs, and there are two triplets. One with a smaller J value, only smaller J value. That means a coupling with meta protons, J4 couples only, and one only with ortho protons, triplet. So the question of ortho is ruled out. Let us look to the meta. Para was already ruled out long ago. And now meta, yes. Meta, yes. This proton is J4 coupled meta to the meta protons. Same coupling constant 3 only, so this will be a triplet 1 plus 1 2 plus 1 3 triplet with coupling constant 3. And this one is a dt not td, because the J3 coupling first, larger coupling, and then meta coupling is 3, so doublet of triplet. And this one will be the 2 J3 coupled protons, so triplet, and J5 is 0, so simply it is a triplet of 7 Hz J. And this one like this will be again a dt, J3 coupled with 7 Hz and J4 coupled meta coupling 3 Hz at their respective positions. So we can assign their data from the given ppm value. We can then the question arises before assigning the ppm values. Delta in ppm is very easy because the triplet is only 1, dt there will be 2, but we know this is electron withdrawing group, so the more desilted one, a greater delta 1 will be here, smaller delta 1 will be here, and the triplet data will immediately write for this one, and the 3 Hz triplet data, that ppm will be for this proton. So we can assign the proton peaks very easily once we know the patterns. Now then question arises whether it is ethyl here, methyl here, or methyl here, ethyl here. If I show you the data here, you will be put into confusion because yes, I show you the table where the CH3, CH2, CH, CH2 adjacent to a aromatic ketone is about 2.8, CH3 is 2.5, and CH2 directly bonded to the benzene ring is 2.6 and methyl is 2.3. So they are more or less similar. You can't say that methyl directly bonded is little less than the the ethyl bonded, I mean the methylene group bonded to the carbonyl group. So that is 2.7 and 2.6, and this is 2.2. So these are very close data, and we have the mass. There will be no mass data, I mean fragmentation pattern data. Then you would have a blind choice. Well, yes, this one will be the most likely structure, that this one should be a singlet because 2.331, and this one is little more. It should be, according to the table, correlation table, it is about 2.6. We found that, and I don't know where from this data has come. If it is reliable data, then yes, it is 2.4. It is larger than this, but I suspect this should be 2.6. But I have to analyze the data that was posed in the question paper. So on this, only on this consideration, we can't say this is the correct one and this is the wrong one. There should be ethyl here and methyl here. So mass spectrum, the data 119 is the best pick, and 57 is another prominent pick that can be only possible with this structure. By the loss of the ethyl radical CC bond next to the heteroatom, the alpha cleavage, putting a triple bond plus charge and a lone pair, this one, loss of 29 is nothing but the 119 is the best pick. And loss of the entire this one, where, I'm sorry, where the alpha cleavage occurs here, loss of the methyl phenyl radical, that will give you the CH3 CH2 Cu triple bond O plus lone pair. That is 57 pick, right? So that suggests that undoubtedly the structure is this. What is this? This is 3-methyl phenyl propan-1-one, 1 2 3 propan-1-one, right? 3 in between parentheses, 3-methyl phenyl and this is propan 1 own, not this one, right? So I've shown you the fragmentation pattern. This is alpha cleavage, loss of ethyl radical will give you this base peak 119, and the loss of the entire methyl phenyl radical will give you this 57. Had it been, a methyl here, had it been only methyl here, the loss of methyl would not have given you 119. So the I've shown here that other meta-isomer, the loss of methyl would have given 133 peak. 148 minus 15 would have given 133, but there is no 133. And the loss of the ethyl phenyl, that means only the CH3CO, had it been CH3 alone, that would have given 43 peak. No 43 peak, no 133 peak, instead 119 and 57. That speaks volumes of the structure of this one, not this one, not this one. This is this one, right? So is it not interesting? So I have just put the values, triplet with 3 Hz, 7.77. I didn't do anything. I just copy pasted, the data, double triplet. But only thing I did consider that out of, these two, 7 is upfield peak, will be near to a electron donating group, and the downfield 7.57 dt, that will be near an electron withdrawing group. And this is triplet with a larger coupling constant will be associated with 7.44 is data. I'm not, and 7.77 with smaller J value 3 Hz will be this proton triplet. Now the answer, I made it little complicated just to explain things. I don't think it is complicated, but it is a little more subjective type. So that what happens here, there are 4 choices. So you have to eliminate ortho from the aromatic patterns. These 2 ortho, they are eliminated. And then competition between these 2 meta. And that will be confirmed by the mass spectral data. So that is the end of our program today. And how did you like it? And I told you every week I will try to put a video on organic spectroscopy problems. After some time, we'll be taking up the theory. So keep tuned and keep liking the video if you have really liked and come up to this stage at the end to listen to me. And also subscribe. If not subscribed, that then you get the information once I produce a video. Of course, I produce videos for all classes. I mean, like the school students also I produce, but you can just see it is for class 10, class 9, class 8. So you just ignore. And for PG2 NetGet, just click on. Bye-bye.